All right, so let's see here. The end of Friday, we did intro to acids and bases. We talked about what makes an acid, what makes a base. So a continuation of that is talking about how do we measure the concentration of acids and bases in solution. We use something that's called the pH scale. Anyone happen to know what range the pH scale works from? Yeah, it goes 0 to 14. Whereas 0 is the acid end of it and 14 is the basic end of it. So the more acidic, the lower the number, the more basic, the higher the number. How we get pH is a measurement of the negative log of, what's this H plus guy called? Proton. And so we're measuring the protons in solution, which is really we're measuring how acidic, right? Because acids are the things that have protons to give. So the higher this concentration, when you take the log of it, becomes a smaller number. So it's really the smaller the number, the more protons. That makes sense in your head. All right, we haven't used this notation before, but this bracket, when I have a bracket around something, it means concentration in molarity of whatever's in the bracket. So in this case, I'm looking at protons, proton concentration in molarity. So whatever's in the bracket, use molarity. All right, so go ahead and get your calculators out. We're going to be kind of calculator heavy today. And what I want to figure out is what are the pHs for these solutions? So let's first think through it. Vinegar, based on what you did in lab last week, is it an acid or a base? It's an acid, right? It's really acetic acid. So would we expect it to be close to the 0 or close to the 14? Close to 0. What about ammonia? Is that an acid or a base? It is a base, so we would expect it to be closer to 14. All right, so let's figure out what these are. Depending on your calculator, you have to put the order of operations are slightly different for every calculator. On this one, we have this version. Let's see if I can get without. I can just type in negative log 1.6 to the negative third. Other ones, you have to type in the value, then hit log, then make a negative. Just whichever one you have.
Wait, can you do that again with that calculator?
Sure. Let's see if I can do it without any glare. Is that good? Negative log 1.6. So that's, there we go, 2 point. So the SNP and figure rules for logs are super wacky, so we're just going to go with 2 decimal points. Did everyone get 2.79? Okay. So you're going to type in negative log of this value, and then do it for the other two. Negative log of 1 times 10 to the negative 7th, negative log 1 times 10 to the negative 11th. Do these values make sense with what we said like 2 minutes ago? Yes, that this is an acid, so it has a pH 2.8, pretty low. Pure water is considered the exact middle, so it should be between 0 and 14, so it's 7. The ammonia being a base, it's going to be closer to 14 on the basic side. Questions about that? In that case, let's put that into practice by doing some titrations like you did last week in lab, and then figuring out how to combine our acid-base knowledge with our balanced chemical equations along with predicting pH. Good. All right, so acid-base titrations like you did last week is a way to determine the concentration of a either dissolved species or percentage in a mixture. So in part A of the lab last week, right, you knew KHP's concentration, and so you could figure out the molarity of sodium hydroxide. And then part B, you knew the molarity of sodium hydroxide, you could figure out the percentage of acetic acid in solution. So you can use titrations in both ways. So titration requires you to know the volume of a standard solution. Right, so that's usually the thing in the burette. And you need to know how much is going to react with what's in your sample. And the sample is usually in the flask. So your titrant is your standard solution, typically. All right, and the burette was this guy. Where you added the sodium hydroxide to 0, and then you measured how much you poured at the bottom, right? So that is the thing being titrated into. So that's the thing being added to the analyte. And the analyte is the thing, solution in the Erlenmeyer flask. This typically is the thing you're trying to figure out. You don't know the concentration, but you know how much you added in terms of liquid. You know how much volume you added. So you can figure out the concentration afterwards. All right, so when we titrated last week and you added the titrant to the analyte, ooh, that's not right. How did you know the reaction was over? Turned pink, right? You reached the end point. So there's two different things going on in an acid-base titration. There is something called the equivalence point, where the number of moles of acid equals the number of moles of base, right? When you're thinking stoichiometrically, the two reactants have the right number of moles to completely react. That is different than the end point. The end point is indicated by a color change of some sort. Last week we used phenolphthalein, which changes to pink. There's about 6 or 7 other acid-base titrations you can do, and they change to blue, or they change to green, or there's a color change of some sort associated with them. So the equivalent point is determined by the stoichiometry of the reaction. But the end point is not at the equivalence point. It is just beyond it. In our situation, we weren't going for super accuracy. So it was okay if you over-titrated by a little bit. It turned kind of light pink to fluorescent pink, you're in the right zone, right? Because we're just learning how to titrate. But if we were really looking for the equivalence point, we would recognize that the end point is just slightly past it. Because you have to add, in our case, a little bit more base past the equivalence point to get it to turn pink. Because it turns pink in basic solution. So you have to add just a little bit more to get to those. They're not the same. So we're going to be in this class looking for equivalence points. Where do they stoichiometrically equal each other? So if we are going to look for the equivalence point, which is determined by the stoichiometry of the reaction, it means we should look at some reactions and figure out their stoichiometry and then figure out the endpoint, equivalence point. All right, here we go. So the question is, what volume of sodium hydroxide is required to titrate 25 milliliters of a 4.5 molar sodium or sulfuric acid solution? How do we go about figuring out the stoichiometry of the reaction? What are the two reactants? They're in the problem. Good. The two things that are given are the two things they're reacting. All right, sodium hydroxide, acid or base? Base, strong base, weak base. It is a strong base. All right, sulfuric acid, acid or base. Good, acid, strong acid, weak acid. It's a strong acid. So I now have a strong acid reacting with a strong base. What do I make? Salt and water. All right, so this is going to donate a proton to this guy. Then I'm left with this. What is not right over here? The charges are funny, right? Because sodium's definitely a +1 and sulfate's definitely a -2. So what have I not done correctly? Did I make the right ions? I didn't, right? How many protons does this guy give up? 1. I lost it, right? So that is a common mistake, that you give away too many protons because you know you need to make water and you recognize sulfate as the other ion. But it should be sodium plus and the HSO4 -1. Now we're balanced. There we go.
So sodium plus HSO4 or just?
Oh yeah, sorry, the plus got. Yep. So I have a sodium ion and an HSO4- ion.
Is the HSO4 an acid or a base?
It would be acting as a, well, it can do either. Because it's acting as a weak acid, could donate another proton, or it could act as a weak base and accept a proton. So it's amphoteric.
So H is a proton.
H plus. So this is, it's a funky example because it can go either way. So. All right, so now I have my balanced chemical equation, right, which is always step 1. Assuming now we have a balanced chemical equation, what is the next step we always need to figure out? Are these balanced in grams or milliliters or molarity, or what are these units in? Moles. How do I get to moles? What do I want to find? What information do I have moles about? right? Who can I figure out moles about? The sodium hydroxide or the sodium or the sulfuric acid? Right, we can figure out moles of sulfuric acid. All right, how do I go about figuring out moles of sulfuric acid? Which units do I start with, the milliliters or the molarity? Start with the milliliters, right? Because it's not a compound unit. It's just milliliters by itself. Do you want me to show you how to get to liters? You can do it in your head? Okay. All right, so molarity is moles over liters. So do I want to multiply by 4.5 or divide by 4.5? If I put 4.5 moles over 1 liter, would the liters cancel out? Yeah. Let's see, what is that? How many significant figures do I get in my answer? 3. Am I done? Is this the end of the problem? No, what are we looking for? Sodium hydroxide. So how do I use this information about moles of sulfuric acid to get the information about sodium hydroxide? Right? What ratio do they have? 1 to 1, right? So how many moles of sodium hydroxide do I need? Same. All right, so now I'm in moles of sodium hydroxide. How do I get to milliliters? Oh, yeah, sorry. No. That's because I wrote this down wrong. This is what I usually do on my working pencil. Okay, there we go. All right, how do I use my moles to get to milliliters? What piece of information did they give us that can help us finish the problem? The molarity, okay. All right, so if I have 1.420 moles per liter, do I want to put the 1.4 on the top or on the bottom? Bless you. How many significant figures do I get to keep? 3. Am I done now? Based on the question, am I totally done? No, I need to be in milliliters. And you can certainly do this all in one step. You don't have to break it down into 3 individual steps, just like we did when it was grams, or when it was moles, or when it was volume, whatever. You can certainly just do it all in one step. This is just kind of think through how to solve it. Questions on that one? Okay. Let's do the challenge one then. All right, so what volume of hydrochloric acid is required to titrate, what would I call this? Sodium carbonate, all the way to the equivalence point. All right, so again, we're going to have HCl. Sodium carbonate, should that be a solid or an aqueous? Aqueous, right, because it has sodium in it. All right, hydrochloric acid, strong acid, weak acid, strong base, weak base. Strong acid. What about sodium carbonate? Do we know anything about it? Is it on your list of 9 strong things? It is not. But if I already have a strong acid, is this going to be an acid or a base? It's going to be a base, and if you don't know anything about it, it must be a weak base.
What makes it have to be a weak base?
It's not one of your 9 strong things. So there's only 3 strong bases: sodium hydroxide, potassium hydroxide, and lithium hydroxide. It's not one of those 3, it has to be weak. And we already have an acid. So by process of elimination, it has to be a base, and it's not one of those 3, so it's weak. So this chapter is like a lot of just thinking through stuff. All right, I have a strong acid and a weak base. Do I have any great rules about what I'm going to make? You should know at least one of the products. It's a go-to. Water, definitely a water. And there will be a salt. It happens to be this salt. We haven't talked about this kind of reaction before, so we're just kind of working through it. This is a gas evolving reaction. They're funky. All right, so I'm going to tell you for sure that these are 2 of the products. Justin.
Does your arrow need to go facing back to the original, like both directions, the weak base?
No, because I'm reacting with a strong acid. And so if it was the weak base by itself, dissolving in water, then yes, I would have double arrows. But because it's a strong acid reacting with a weak base, it's going to go towards completion. So, Sarah.
Would your third product be CO2?
It would be CO2. That's what's left. Am I balanced? No. What do I need to do to balance this guy out? Okay, if I do 2 HCl's, then what? All right. It's like all coming together. Predicting products, balancing, strong acids, weak acids, stoichiometry. This is why there's only 2 chapters on the test, because they're pretty thought-provoking chapters. All right, now we're ready. We have a balanced chemical equation. Where did we get started? Because in the previous one, I gave you milliliters and molarity. This one, I gave you grams and molarity. I want to find moles, right? That's always the first step. So do I find moles of the HCl, or do I find moles of the sodium carbonate? If I start with moles of HCl, I have moles per liter, but do I know anything about the liters? No, that's what I'm looking for. If I start with grams, how do I get to moles based on grams of sodium carbonate? Molar mass. Yep, and I'll go ahead and tell you that the molar mass Na2CO3 is 105.9 grams per mole. All right, do you guys want to do this all in 1 step or 3 steps? Doesn't make any difference to me. We'll do it all in 1, why not? All right, so we're going to start off with the information that we know. All right, so now I'm in moles of sodium carbonate. How do I get to moles of hydrochloric acid? The ratio, okay, do I put the 2 on the top or on the bottom? So I'm looking at this ratio. Put the 2 on the top. All right, now what units am I in? Moles of what? HCl. If I want to get to milliliters of HCl, what do I need to use next? The molarity. So do I put the 0.995 on the top or on the bottom of my equation? On the bottom, right? Because we want those moles to cancel out. Would I stop there? I could stop there, or I could go all the way to milliliters. All right, let's see what that is. How many significant figures do I get to keep? Not 4. 3, right? This only has 3. That has 4, that has 4, but this only has 3. So 42.6. How am I feeling about that? It's what we've done before, it's just thinking through it in a different kind of way. All right. No one has a question? All right. Originally, next I had these redox reactions. I'm going to save that. I will come back to this. So if you're looking at the slides, we are going to move ahead to, let's see, what is after this? Oh no, I got time. I can at least start this. Let me do redox reactions, at least a little bit. On Wednesday, we're going to start chapter 6. So bring your chapter 6 slides on Wednesday. All right, redox reactions, which are my favorite thing on the entire planet, so it hurts me that we can only spend 15 minutes on it. Tragic. But luckily, in 109, I spent 3 weeks on it. Yay! All right, oxidation numbers. This is what we've been talking about when we have an ion, right? When I say sodium has what charge, you're like, +1, that's its oxidation number. Just a fancy way of naming that little charge it has. And we need it when we're looking at, right, 2 nonmetals reacting with each other, like sodium chloride. You have to know, okay, sodium is going to be +1, chloride is going to be -1. All right, they're 1 to 1, right? So we've been using them, but just not naming them as oxidation number. So the oxidation number of an atom is the charge it would have if it became an ion just floating around the solution. And so we use these to figure out, yeah. All right, we've been using oxidation to be able to predict products. In all those precipitation reactions, right, the only way you can predict the product is knowing, oh, SO4 is always -2, so I need 2 potassiums to balance that out. So we know the oxidation numbers, we just haven't used them. Let's see what I have on here. So we're going to be looking at oxidation numbers. We are looking, yeah. So we're going to be looking at oxidation numbers to be able to predict which atoms are likely to become cations or anions. If I'm a cation, have I lost an electron or gained an electron? You've lost one, right? Because the cations make you feel warm and fuzzy, so these are the things that are positively charged. Because everybody loves cats. If you don't, pretend for the rest of the semester you at least appreciate cats. So cats make you feel warm and fuzzy, so they're positively charged, which means their electron has gone someplace else. Anions are negatively charged, so they have gained an extra electron. So what these reactions are is electron exchange reactions. All right, so in order to become an ion, you got to become, one has to become plus, the other one has to become minus. So the electron has moved from one atom to the other atom. So oxidation reduction refers to the fact that oxidation is the loss of an electron. If I have lost an electron, what is my charge going to be? If I was 0 and I gave away a minus, I'm now plus, yep. All right, so oxidation produces a cation, and reduction produces an anion. So then we pair them to see where the electrons have gone. All right, so just like in an acid-base, you have to have one acid with one base. An acid gives away a proton, the base takes the proton. So you have to have them in pairs. You can't have two acids together. You can't have two bases. You have to have one of each. So let's look at two partial reactions, and then we'll put them together. Oh, question, Abigail.
Could you just do that?
Yeah, oh, sorry. Oh, there we go. All right, so here is my two partial reactions. In a real reaction, there shouldn't be any electrons left over. All right, having electrons as a product is funky. It doesn't actually happen. But we're going to pretend. We're in pretend chemistry space. All right, so let's say I have iron as a solid. If I have a normal element off the periodic table, what do we always assume its charges? If I just pulled magnesium out, we would assume it's 0, unless I tell you otherwise. All right, so iron, we give it a charge of 0. If it gives away 2 electrons, what is its new charge? 2 plus. All right, so now I have iron 2 plus. Is that a cation or an anion? It's a cation. So we can rewrite this. I now have made a cation. If I have become a cation, did iron become oxidized or reduced? It became oxidized, right? Because iron was 0 and became plus 2. It lost electrons. It became a cation. All those things put together. So we would say in words,
Isn't it rusted?
that is a, in general, yeah. Yeah. All right, so I would say the iron was oxidized. So it went from 0 to plus 2, became a cation, lost electrons, all those things. All right, best guess. What do you think reaction is going to have next? If I already have one of these. We're going to look at a reduction reaction. There's only 2 options. All right, so now I have hydrogen with an unknown charge, mystery charge. Gaining 2 electrons to become hydrogen gas, which has a 0 charge. what charge would the H's have? Positive 1, right? There's 2 of them. So I would say it's 2 H pluses plus 2 electrons become H2. What's an H plus called in other lingo? Starts with a P. Proton. I have 2 protons gaining 2 electrons to make hydrogen gas, just plain old hydrogen gas. All right, so I've gone from +1 to 0. I have now done a reduction. So we would say in words, the proton or the H plus was reduced. You can think about in that it reduced its charge, right? It was +1, it went down to 0, it had a reduction in charge. You can think about it in terms of it gained 2 electron. All correct. So you have enough time for your quiz. I'm going to save this one last slide for Wednesday, and then we'll start chapter 6, which is thermodynamics, heat transfer, work, baby physics, just a smidge.